Okay, so today we'll work on the differential equation for the harmonic oscillator. Just solve the differential equation in more conventional ways. Okay, so we'll go through the standard solution procedure for this differential equation. I'll go through it because we'll also need it when we do the hydrogen atom. A different differential equation, but the solution procedure will be somewhat similar. Okay, so what do we have for our equation? We have the Schrödinger equation minus h bar squared over 2m d squared dx squared plus 1 over 2k x squared. So all of this is the Hamiltonian operating on u, gives me e u, where u is a function of x, right? Okay, so what we do is we look at the large x behavior of this function. Okay, so large x behavior is when this x is so large that a similar term becomes negligible, so that I get a simpler equation. For example, here I have something x squared multiplied by u, whereas here I have a constant multiplied by u. So if x is sufficiently large, this term will be much larger than that term. Okay, so what I do is then as an approximation, I say, well, in that case, minus h bar squared over 2m d squared dx squared u plus 1 over 2 k x squared u is approximately 0. Okay, so I'm going to take that term to be negligible compared to this term. Then I have a simpler equation. Okay, so I have d squared u dx squared is approximately m k over h bar squared x squared u. Yes? It doesn't go to 0. It becomes much smaller compared to this term. Okay, so I have two terms. One of them is 1 over 2k x squared u. The other one is e times u. Okay, so for very large x, this is going to be much larger than that because x squared is going to grow where e is a constant and it will, okay, have a certain value. So what I do is I neglect this term, okay, compared to this one. Okay? All right, so I get an equation like this, which says that the second derivative of u, when I differentiate it, gives me something like x squared, okay, times u. Can you guess what type of function would do that? Whenever you have derivative of a function, yes, okay, so you think about exponentials, and each derivative is going to bring something like an x. Actually, it's going to be a little bit more complicated than that, but let's see. So if I just say, suppose u is some function which goes like e to the, let me say beta x squared, let me also put the 1 over 2. Okay, I put the 1 over 2 into beta also, but this makes my differentiation a little bit simpler. So u prime is going to be, I shouldn't say equal to, because this is now I'm saying this is approximately as a result of this equation. Okay, so u prime is going to be beta x times e to the beta x squared over 2, right? One more derivative, then what happens? U double prime becomes something like, okay, derivative of this term, which gives me beta, but also derivative of this term, which again brings down a beta x, so it's going to be beta squared x squared times e to the beta x squared over 2. Okay? So I'm almost there. There's this, instead of just something times x squared, I have also this constant term. But remember, I'm just looking at it in the large x limit. This is going to be much smaller than that when I increase x a sufficient amount. Yes?
By the way, beta is coefficient of mkx squared divided by h squared, right?
No, beta is a constant at this point. Okay, so now we have to identify what that corresponds to. Okay? So now, so this is okay now. Second derivative of u, as we have seen here, is something times x squared. So that means I can choose a beta. So if beta is equal to the square root of this, so it can be plus or minus square root of mk over h bar squared. Okay, this is satisfied in the large x limit. So in the large x limit, when x is very large, the function behaves like, okay, a linear combination of e to the beta x squared over 2 and e to the minus beta x squared over 2. Okay, so if I choose the plus beta here, it's going to be a linear combination of these things. Okay? Yes?
How can we determine that u has that kind of solution? I mean, beta x squared divided by 2. How we determine that?
Just guess it. We just guess it. Okay? And then we find out that it is so. Because we are not solving this equation, okay, formally here. This, okay, is not the solution to that. As you can see, the solution is really this, okay? But for sufficiently large x, this is going to be a very good approximation. Okay, so what we see is that this function u as a function of x does something, but or when x becomes very large over here, this is the asymptotic region that we are interested in. In that region, it appears that there's this nice solution e to the minus beta x squared over 2. Okay? Unfortunately, there is also an e to the plus, okay, beta x squared over 2, which I do not want, okay, because that's something that's going to diverge as x goes to infinity. All right? Okay, so what I do is I say, okay, let me just make a some sort of, give some sort of form to this u. I'm going to say that this u is going to be equal to some function h, okay, times e to the minus beta x squared over 2. Okay, so I can always do that. I can just multiply, just factor this function into two forms, and of course I have to find what this is. Okay, but the logic in all of this is that you hope that by extracting this behavior for large x, which you see is something not so simple, e to the minus beta x squared, what remains here, h, is hopefully will be a simpler function, okay? So that we can solve this more easily. Okay, so what, yes?
Is h, it's just a function of x, right?
Yes, at this point it's a function. I'm not putting in x explicitly because I'm going to transform the variables at this step. Okay, so this is the form. In fact, what I'll do is I'll write this as h of, okay, obviously it depends on x, but minus 1/2 x over x0 squared. Okay, because I know that this thing, whatever it is, has to be unitless, right? It is function of a quantity. That quantity has to be unitless, and you can check easily that that means that, okay, beta is equal to 1 over x0 squared, and beta was equal to what? Square root of mk over h bar. Okay, so that's the form when x becomes very large. All right, so what we are going to do is now I'm going to transform the equation into an equation in terms of, again, a unitless quantity. So I will write the whole equation in terms of x over x0. Okay, so this is just transforming the variable x to a row, so that it's going to be unitless. And I'll hopefully again obtain a simpler equation. Okay, so let's do that. What happens? X goes to rho times x0, but the only dependence on x is x squared, so x squared goes to rho squared times x0 squared. Okay, and I'll just, instead of rho squared x0 squared, I'm just going to write rho squared, what? X0 squared is h bar over square root of mk. Okay? So that's that. Okay, so let's just transform the equation. I have, now I go back to my equation. It says minus h bar squared over 2m, two derivatives with respect to x, which means I am going to get what? Let's see. D squared, the rho squared, and so I'm going to get an h bar, please check my algebra, h bar square root of m k. Okay, so this thing is just d squared dx squared. Okay, so I have transformed from rho to x. Okay, all I did is instead of x, I put rho times x0. All right? Plus 1 over 2 k x squared. So in place of x squared, I'm going to put in rho squared times h bar square root of mk. Okay, so this piece here is just x squared. Okay, so I change my variable from x to rho. Okay, times u, okay, is equal to EU. Okay, but let's just now look at those terms one by one. You see one of the h bars go away, and I end up with minus 1/2 h bar square root of k over m d squared d rho squared plus 1 over 2 okay, h bar square root of k over m rho squared. Okay, u equals e u. All right, yes.
I couldn't understand why did we put h there.
Where did you put h where?
At the beginning, like u equals to h.
Okay, this is not Planck's constant, by the way. Okay, I'm just factoring, let's call this something else, f, okay? So this is going to be some f of x, okay? So I can always factor a function, okay, into y because it's going to make our life easier, okay? So the reason we do this is we have found out that this function u behaves like this for very large values of x. So if I now factor that out, okay, this function f, I am hoping, is a simpler function. Okay, it may not be true. This is one thing that you try, and we'll do this again. As I said, when we solve the hydrogen atom, we'll again look at the asymptotic structure very near the origin, very far away, and factor those parts out. And then in the middle, okay, we will have some form which will satisfy a simpler differential. So this is a trick which works very nicely for a large class of ordinary differential equations.
So for that case, we were asymptotically saying this is the function form, and it's no longer approximation, right? It's equal right now.
Yeah, okay. So this is obviously the exact equation. And we are going to put in the exact form right now, okay? So that's what we are going to do. Okay, so yes.
How can we say that this is exact solution? Because we just approximated the beta. We obtained the beta by approximating the solution.
Yes, okay. So I think there's some confusion about how come I can write this as an exact solution. Now, you see, this is the asymptotic form, okay, some approximation when x becomes very large. So I put that over here, and then I say this f is whatever is needed to make this the exact function, okay? I could do other things. I can multiply this also by sine x if I like, okay? It will still be a solution as long as I can find f, okay? So the problem is now transferred into finding what f is. Instead of trying to find u, what u is exactly directly, I am now trying to find this f, okay, which will make this u exact. Okay, so in fact, we'll substitute this into the full equation. So this is now, you see the full equation, no approximations here, except that I'm just transforming variables so that things are going to be simpler. In fact, you can see that I already get these classical frequency of oscillations here, right? And that, again, if I just now go ahead and divide the whole equation by 1/2 h bar omega c, what do I get? I'm going to get minus d squared d rho squared, okay, plus just rho squared u is going to be equal to e over h bar omega c over 2 times u. Okay, so I still have the full exact equation. The only thing I have done is I have transformed the variable from x to x over x0. Okay, so I've just gone, I have scaled the variable so that it's nice and unitless. Okay, now it's time to do the hard work. Okay, so the hard work is now putting in this object. Okay, so our u is now going to be some, okay, h of rho e to the minus rho squared over 2. And I'm going to put that into the equation so that I make sure that this is going to satisfy that equation. Okay?
Wasn't the F,
Hmm?
wasn't the F equal of A soft rho? Yeah, soft rho.
Again?
I mean, wasn't you
Okay.
rho?
Okay, let's change it to F because I think sometimes H is confused for Planck constant. Okay, so let's put it F. Okay, customarily its name is H though because it will turn out to be a set of polynomials named after Hermite, so people call it H, but okay, we'll call it F for in honor of one of your friends whose name may start with F. I don't know who. Okay, so I need the second derivative of u, right? So let's just start differentiating. So I'm going to get u prime, which is the first derivative with respect to rho, is going to have two pieces. Okay, there's a rho inside this f, and there's a rho there. So it's going to be f prime. Please check my algebra. I make lots of mistakes here. Minus just rho f, right, times e to the minus rho squared over 2. All right, that's the derivative of u with respect to rho. What about second derivative? U second derivative. So now I have to differentiate this, which gives me f double prime minus f minus rho f prime. But then I also have to multiply this by the derivative of that, so that's going to be minus rho f prime minus rho f, right? E to the minus rho squared over f. Okay, so there are two terms of rho f prime which I can combine together. In fact, let me do it. Okay, so this is going to be f double prime minus rho f prime, 2 rho f prime. What else? Minus rho squared, oops, okay, minus f plus rho squared f, right? Please check my algebra.
I think instead of rho squared over F, we should have rho squared over 2.
Hmm?
I mean, why do we have rho squared over 2 in the second derivative? We have yes.
Okay. All right. Now we have to put all of that into this equation. Okay, before I do that, let me just make this first term positive and such things. So let me just rewrite this equation. Okay, I'm going to just basically multiply this by minus 1. Okay, so I'm going to get d squared d rho squared u, okay, minus rho squared u. Okay. Now this thing I'm going to bring to the left hand side, so it will be minus, but then I'm also multiplying by minus 1, so it's going to be plus. Okay, this whole thing, you see, this is also very nice and unitless. I'm going to call epsilon. Okay, so epsilon is 2e divided by h bar omega c. Okay, so I'm going to get epsilon times u is equal to 0. Okay? So let's now put in this derivative where it belongs into the equation. All right. So we have f double prime minus rho f prime, okay, minus 2 rho f prime, and then I have minus f, okay, plus rho, okay, plus rho squared f. Okay, times e to the something, but everything is e to the something. So let me just put this in, minus rho squared f, okay, and then plus epsilon f. Okay, so this whole thing multiplied by e to the minus rho squared over 2 is equal to 0. Okay? So I can just cancel this term, which is common to all of them. And you see this rho squared f cancels that minus rho squared f. Okay, this is not accidental. Okay, that's because we have chosen this asymptotic form based on this term, right? Remember, we just put in 1 over 2 kx squared and solved the equation and obtained this form. Okay, so when we put this type of dependence, that part of the equation, okay, which corresponds to large rho, remember we derived this for large x behavior, so the large rho term here from which we derive this term cancels. Okay, so that we hope is going to lead to some sort of simplification of the problem. Okay, so that's now our equation that we need to solve for f. And the idea is that hopefully this is a simpler sort of function which we can solve more easily, and the first thing to try is to try some sort of power series solution. Okay, so we say that suppose this f of rho has a form n from 0 in general up to infinity. Okay, some of the coefficients may be 0, but in general it's a full series. So it's c n rho to the n. Okay, so we assume a solution of this form. So we'll need the first derivative and the second derivative of this. So the first derivative is going to be equal to n from 0 to infinity Cn n rho to the n minus 1. In fact, we need really rho times f prime, so let me write that. Okay, rho times f prime is n from 0 to infinity Cn n rho to the n, right? What about the second derivative? Well, f double prime of rho is going to be equal to sum n from 0 to infinity, okay, Cn n, one more derivative, n minus 1 rho to the n minus 1, n minus 2. Okay, so now that's my series. Okay, so now I'm going to put all of these things into this equation, but I would like to have all of the summations with the same limits on the, okay, summation. So here I have from n0 to infinity, here I have n0 to infinity rho to the n, so those are very nice. They will fit very easily, but here I have rho to the n minus 2. So I want to convert this to rho to the n also, so that I can just bring them under the same summation and factor out a rho to the n. So what do I do? Since this n is a dummy index, I just replace this n by n plus 2. Okay, so I just make a transformation instead of this n and all n's here, I put n plus 2. Okay, so I'm going to put n plus 2 for all of the n's. Okay, I'm just making a transformation saying that n, instead of n, I'm going to put n plus 2 because this is n is a dummy index. Okay, I can shift that, so I have to do it all over the place. Also here also. Okay, so this n also goes to n plus 2, which means now I have to sum this over. Okay, n plus 2 equals 0 means n is equal to minus 2 to infinity. C n plus 2, n plus 1, n plus 2, rho to the n. Okay? So now you might say, well, what does this n equal to minus 2 mean, etc.? Well, Cn is well defined, but you see for n equal to minus 2 and n equal to minus 1, these coefficients are 0 anyway, right? So I don't really have to start this from n equal to minus 2. I can start it from n equal to 0. Okay? All right, so this is just playing around with indices. Okay, so now let's write this equation in full. So I'll write this as a series. So this is going to be summation n from 0 to infinity. Yes?
I don't understand how you changed n to 0 from -2.
Okay, because if you have n equal to minus 2, you see n equal to minus 2 term is 0. When you have n equal to minus 1, this term is again equal to 0. So the first contribution that comes is coming from n equal to 0. Okay? All right, so let's now just put these things together. So f double prime is c n plus 2, n plus 1, n plus 2. Okay? I'll have a big sum, then I have rho to the n over here. And then I have minus 2 rho f prime. So it's this term. So it's going to be minus 2 n times Cn. Okay. That 2 is this 2. And then I have epsilon minus 1 times f itself. Okay, that's easy, just Cn. All right, so please check my algebra. I make mistakes. Okay, so everything multiplied by rho to the n is equal to 0. Okay, so I want solutions of this form. And since all of these rho to the n's have different behavior, okay, the only way you can have this equal to 0 is if this coefficient is 0. Okay, so I'm going to get this thing equal to 0 for each n. So for each n, this is going to be 0. And that means I'm going to get C n plus 2 times n plus 1, n plus 2 is equal to, okay, moving things on the other side, 2n Cn plus 1 minus epsilon Cn. All right? Or C n plus 2 is equal to what? 2 n plus, let me see, yeah, okay, 1 plus epsilon, 1 minus epsilon, okay, divided by n plus 1, n plus 2, Cn. Okay, that's very nice. We get this nice recursion relation, which when you are given Cn, you can find out what Cn plus 2 is. So you see the equation is separated into two types of functions. You can have C0 equals something and C1 equals 0. So if C1 is 0, that means C3 will be 0. And okay, so all of the odd terms, C3, C5, C7, they'll all be 0. And C2, okay, in general, C2, etc., everything is not going to be 0. So that is going to be an even function. So there will be an even function of rho when I choose C1 equal to 0, so that rho to the 1, rho cube, rho to the 5th, rho to the 7 will all have 0 coefficients. Or I can do the opposite. I can get an odd function. If I put C0 equal to 0, that means C2 and C4 and C6, okay, all of those things will be equal to 0, but C1 can be something finite, say 1, and then obviously C3, that will generate C3, C5, etc., so that will be an odd function. There will be no constant term, there will be no rho squared, no rho to the 4, no rho to the 6, so I'll have an even solution and an odd solution. Okay, so everything seems to be nice, except that I don't know what type of function this is. So let's just try to see what's happening there. Yes? Okay.
Why you make it equal to 0?
Why we make what equal to 0?
This equation above.
This equation, because that's the differential equation, right? So there's our differential equation. It's this one here. Okay, the right-hand side is 0. All right? Okay. So, yes.
How can we say that let's take C1 is equal to 0 or C1 is equal to 1?
Okay, so these are possible solutions. The equation will be satisfied for any set of C's which satisfy this equation. Okay? So I could say take C0 equal to 0 and C1 equal to 0. Again, the whole equation is satisfied. But what do I get then? I get a function which is all zeros, which again is satisfied. Okay, if you put 0 into the equation for u equal to 0, the equation is satisfied, right? But it's not useful. Now, I can just put in C0 finite and C1 equal to 0. It will generate a solution like that. So it will be a solution to the problem, okay? But it will be an even solution or an odd solution depending on which one you choose, okay? So anything that satisfies this recursion now is going to satisfy the equation, all right?
Can we put both to 1?
Yes, you can put both to 1, then it will be a just linear combination of an even and an odd. But we'll see, okay, that we cannot really get away with any choice. So that's what we are going to look next. So let's look at, okay, so let us look at large n limit, okay, of these Cn's. Okay, so for large n, you see Cn plus 2 becomes what? How does it scale with n? Can you tell me? If n is very large, what do I get? What is the relationship between Cn and Cn plus 2.
Approximately it's approximately 2 over n.
Yes, okay, so in the limit n becomes very large, this term becomes very large compared to this term. Okay, so the numerator becomes approximately 2n, and denominator, this term is approximately n, that term is approximately n, so it's 2n over n squared, right? So it is 2n over n squared, which means, okay, it's 2 over n Cn.
So Cn is approximately C times 2 to the n over 2 over square root of n factorial.
Well, okay, let's see. Okay, there's an easy check of this. Let's see, okay, let me say consider. We'll see why I am considering this. Consider the function e to the rho squared, okay? What type of expansion do I have for this, okay? If I make a Taylor expansion, I know that I'm going to get 1 plus, okay, rho squared over 1 factorial plus rho to the 4 over 2 factorial plus rho to the 6 over 3 factorial and so on. Okay, so rho to the 8 over 4 factorial and so on. Okay, so if you like, this is, if you look at the coefficients, this is associated with C0. This coefficient is associated with C1. This coefficient is associated with C2, okay, and so on. C3, I'm sorry, C2, right? This is C4 for the fourth power of rho. This is C6, okay, and this is C8. Okay, so those are the coefficients of the nth power of the rows. So my equation is going to generate a, okay, series like this, and that is the type of terms that I am getting. Now, if you look over here, I am going to get C, okay, okay, so if I look at, for example, C8, it's going to be C6 over 4 factorial, okay? Oh, I'm sorry, just 1 4, right? So if I look at, for example, what C6 is, it's going to be the previous one, C4 divided by 3, right? So what is the general rule? C4 is equal to C2 over 2. Can you tell me what Cn is? Okay, let's just put, okay, Cn is equal to Cn minus 2 divided by, okay, n minus, okay, n over 2, right? Okay, so the ratio of one to the other, okay, so Cn over Cn minus 2 goes like 2 over n, which is exactly what I have here, okay? So what does that mean? Okay, what does that mean for this, for the function generated by these series?
It grows like expansion of the square.
Okay, so this function, if I leave it alone, will be proportional to e to the rho squared, okay? which is terrible, okay, because that's what something we are trying to avoid. Remember how we started this? We said there are these two solutions, e to the minus rho squared over 2 and e to the plus rho squared over 2, okay? And we said we didn't want this, and we tried to get a function which had e to the minus rho squared over 2 behavior.
Why we don't want the other?
Hmm?
Why we don't want the other?
Because we don't want a wave function that goes to infinity, okay, as rho becomes infinite, because rho is just x, okay? So we tried to find an exact solution which had this form, but when you use the exact equation, you still have this solution hiding behind, right? We did not really kill that solution. We just said, okay, let's write our solution in this form. And after we write this solution in this form, let's find the exact solution that this one behaves, okay? That this one satisfies. But now we find out that, okay, this e to the plus rho squared over 2, okay, is like this Frankenstein monster. Okay, we tried to kill it, but it's coming up from the lake again. Okay, so we have to kill it real good this time. Okay, otherwise this will dominate. Okay, this e to the plus rho squared typo. So if this now starts to behave like e to the rho squared, it's just going to generate this form. Okay, and that's something we don't want. So how can we get away with it? Okay, so how can we still use these recursion relations, okay, but not get this full function? Okay, the trick is,
It must terminate at a finite.
okay, the trick is to truncate the series at a certain n. So if you truncate your series at a certain point, then of course you don't have to do this argument of what happens for very large n. Okay, you no longer have e to the rho squared function then, because if you have, for example, just 2 terms, 4 terms, 5 terms, whatever, any finite number of terms, as long as you have a finite polynomial, you are okay, because a finite polynomial times e to the minus rho squared is a very nice and well-behaved function. Okay, so the result of all this discussion is that you should terminate the series at a certain, okay, n. Okay, so when the series reaches a certain value n, we stop it. How do we do this? Well, we have this Cn plus 2 is equal to 2n plus 1 minus epsilon divided by n plus 1, n plus 2, Cn. Okay, if I choose this En in such a way that this numerator becomes 0, the series is terminated, right? So if I have, for example, C0, from that I determine C1, from that I determine, C2, from that I determine C4, but then C6 is 0, then all the rest of the terms, C8, okay, C10, etc., they all become equal to 0. So I am safe, okay? Then it's a finite series. It contains only C0, C2, C4. So how can I do that? Well, I have to choose this epsilon properly. So epsilon must be such that, okay, for a certain value of n, it becomes 0, okay? So in fact, let's make it small n. So if I choose 2n plus 1 minus epsilon sub n equal to 0, so it's going to be different for different values of small n, then Okay, that implies that C n plus 2 is 0. Okay? Because the numerator is 0. So that means En is equal to 1 plus 2n. What does it mean in terms of the energy? Remember that this is energy, 2 energy over h bar omega c. So this is going to be En. So En is equal to h bar omega c dividing through y1 n plus a half. So we get to recover the energy levels that we already determined by applying the operator method. So only at these energies will I have proper solutions that do not go like e to the plus rho squared over 2. Yes?
No, I couldn't understand why we are transferring C as 0.
Okay, because if I don't let it, okay, if I don't carefully kill it and let it become 0, then I'm going to get all of these coefficients finite. And if all of them become finite, then it turns into an infinite series which will go like e to the rho squared. Okay, which I don't want. Okay, so the infinite series, according to this recursion relation, gives you a function which is e to the rho squared. It acts like e to the rho squared for large rho. Okay, which is something I don't want.
Yes, but instead of making it 0, why don't we just say this is a sum from 0 to 100 or something like that?
No, you cannot just do that. Okay, so you cannot just say, let me cut the series off from, I take all these terms from 0 to, okay, 4, 6, 8, and let me stop there. Why? Because if you have a C8, then you must also have a C10. Right? Otherwise, you are not satisfying this equation. Okay, so you have to satisfy the full equation. So for that reason, you have to make sure that this, okay, equation is satisfied for all n. And the way to satisfy it for all n is to make sure that it stops someplace. If it doesn't stop, then you will get into trouble. Okay, other questions? Yes.
Can we say equivalent method is to the rho squared because we could limit it like this, like n doesn't go to infinity.
Can you repeat it?
Can we say equivalent method if we choose e to the rho squared at the beginning because we could limit at the case 2 like this, like and it's not.
E to the rho squared in the beginning? I don't see how that can happen.
Sorry, e to the rho squared divided by.
You want to choose it as e to the plus rho squared over 2 in the beginning? Yes, but that's not a very useful solution. It is a solution. It's a solution to this equation, definitely. But it's not useful because it doesn't give you a u which is normalizable.